All right. Good morning, everyone. So what I have today is just for your amusement. There's not going to be any exam questions about any of this. So just sit back and relax and enjoy the show. And what's that? Wait, you can see this? You just go to Unit 6 if you want to follow. Oh, because the quality of the projection is bad. Let me see if I can. PO Unit 6. Okay, here. So I'm going to be talking about something that I always enjoy, namely looking at parts of programming languages that don't really work as well as maybe they should. Now, programming languages, unlike regular languages, are designed by humans, and so presumably some thought went into them when they were designed, now, which is true for most programming languages, with the possible exception of PHP. But even though a good amount of thought tends to go into these languages, sometimes there are issues with them, that they're surprising in some way, and that they entrap the poor programmer who's using them. And so when I say what's a trap, I specifically mean code that compiles. So if it doesn't compile, it's not a trap by this definition. It has to link. It executes. But then when it executes, it does something different than a regular, normal, sentient human being would think. So I'll give you an example. So have a look at this program here. This is in Java. I'm insulting programming languages today with equal opportunity, so I figure Java should get its share. So let's see. So here we have a language which I took from a very nice book by Josh Block and Neil Gafter called Java Puzzlers, that you should definitely, if you want to spend your summer usefully, get a copy of and work through. So here he has this program that he calls a browser test, or that they call a browser test. So we have main, a regular old main. We print iExplore, I guess because okay, he doesn't like me to insult Java. So we print iExplore, http://google.com, and then we print maximize. So what does this thing do? What do you think? So yeah, on the Mac, would it do nothing? So on a Windows machine, will it actually open up Internet Explorer and show the Google page? I mean, what's strange about this program is it doesn't look like it would compile, right? But it does compile. Otherwise, I wouldn't show it to you. And it does run. So yes, it does really compile. But the weirdness is, why does this stuff compile? Notice this is not inside a system.out.print, right? This is just sitting right there as a top-level statement. It is a statement. So yes, HTTP : is a label. It is a label because Java does have labels. Java doesn't have gotos, but it has labeled breaks and labeled continue statements. And what is the rest? What is this? It is a comment, right? The / introduces a comment. So yes, it compiles, and it runs, and it prints iExplore : maximize, which is not very useful. But the amazing thing is that it compiled, right? So the micro lesson here is that I don't think any of us has ever used a labeled break or a labeled continue. Did anyone? Oh, wow, okay.
And then I said that I should never use labeled.
Right. Yeah, I had to promise my mom never to. Okay, so most people never use these very obscure statements, but there they are, and they're in the language, and they make our head scratch. So that's an example of a trap. This one was not particularly dangerous, but you'll see soon how, in a different context, essentially the same thing can be dangerous. So here you see the little raccoon studying a trap, and for good reason, because when you study traps, because you want to know when you need to be careful when using a language. With some languages, you need to be very careful. Such languages should remain unnamed to protect the guilty. I mean something like C++, for example. And so you want to learn what to avoid when using language, and also when selecting a language. If there is a language out there, such as C++, for example, that is really quite dangerous, you want to know, why are you using it? And also, maybe some of you are going to be in a position where you have to design a new language. And in that case, you want to know what other people messed up in other languages, like C++, for example, so that you stay far, far away from the follies that they introduced. So it is a good idea to look at some of the weaker points of some of the languages to see, A, where to stay away from when you must use such a language, B, to try to avoid those languages, and C, to make sure that if you were ever in a situation where you actually could make the life of your fellow humans miserable, that you also avoid that. So I'll give you an example that you're probably familiar with because you've just gone through 2 semesters of object-oriented programming. So let's see if you find this. Yeah, so the rules are, by the way, if you do study the slides, don't hit the space bar, okay? You have to wait, you have to come up by it yourself, otherwise it's no fun. So here I have a C++ class called employee, kind of a normal class. Here I'm having a print function. In order to save space, I'm making all the functions here inline. So doesn't mean, of course, it's a virtual function, so it won't be inline, but it saves me a couple of lines of space on the slide. So to print an employee, it prints their name. And now I want to print a manager. And so here I'm printing the manager, and I want to print the name. It's a private field of the superclass, so I call print to print the superclass. And then I print the department, so I call the department method of the superclass to get that out. And it'll print, Joe Smith managing sales, or whatever. So what's the problem? It will compile. It will run. And now what happens when I print a couple of employees and managers? Aha! Print does not print the superclass, despite what the comment says. Very good. It's a recursive call. I should have said employee, : print, right? That's how it works in C++. If you want to reach the superclass, if you want to turn off the virtual dispatch, then you have to name the class explicitly. In Java, you would say super.print. So that's kind of a thing that you're familiar with. So here is episode 2. So what's wrong here?
Employee is a label.
Aha, you guys are too good, right? So here, employee : is a go-to label. And this one is much nastier, right? Because it'll compile. It'll run. And even though the programmer tried to do the right thing, namely do the employee : thing, the programmer missed a single colon, and then they get an infinite recursion. Does this ever happen in real life? Yes, like if you teach C++ to people in their second year. When I used to do that, I would have every week someone would come to my office with some code where they said it just hangs, or it dumps core, and they didn't know and this was the reason, that a student was not careful about doing the colon thing. Of course, eventually one wises up and learns that, but it's a little bit nasty that almost no one ever uses even in C. I mean, when's the last time you used a goto label? And I mean, it's just not a very common occurrence, and so it's a little unfortunate that the language here makes that. All right. Now, since we're talking about virtual functions, let's look at something that's a little more interesting. So here I have two classes. I have a shape class, which has some basic things about shape. To keep it simple, I just store the color here. And somewhere I have an enum for colors, and so by default, when one resets the shape, it turns black. Here I have a point class that extends shape. It's a subclass of shape. That's how you write it in C++. The point has coordinates x and y. And when one resets the point, and notice this is a virtual function, when one resets a point, then one resets the shape. Notice here I did correctly have the shape colon. I'll never trick you with this one again. And we set the point to 0. Also, in C++, you recall that when you construct an object, unlike in Java, when you construct an object, it starts out with everything 0, or if it's a Boolean, false. Right? In Java, every object is just zeroed out at construction time. In C++, that's not by default the case. In C++, when you construct an object, how are like integer or double or enum fields initialized? They are not, right? They're just left in whatever state those transistors in memory were there. Why are they not initialized? Because it makes programming in C++ more interesting and exciting. So they're not initialized because presumably the incredible cost of initializing them would make the world slow down to a crawl. So 30 years ago, that might have made some sense. Then, of course, nowadays, the cost of initializing a block of memory is so trivial compared to everything else that goes on that it would be well worth doing, but C++ still doesn't do it. So, fine. So I'm going to make sure that a shape gets properly reset. But it doesn't work. Why doesn't it work? So now when I make a point, it still gets initialized with random coordinates. Right?
Virtual, il est en haut. La deuxième méthode est virtuelle à partir du moment où tu finis virtuellement.
Yeah. Oh yeah. So let's work through it very closely, right? So the point constructor calls the shape constructor.
Non.
So every time that.
Je vous l'ai dit celui-là. Hein?
So the shape constructor calls reset. Yeah. So the difficulty is which reset. And now in C++ does something quite extraordinary. That when you construct the superclass, for that fleeting moment in time, the virtual function table is the superclass's virtual function table. Then when the subclass constructor runs, the virtual function table is swapped out into the subclass virtual function table. So the rationale is that a superclass, that while you're in the superclass constructor, the subclass virtual functions are deactivated.
There is no dynamic binding in the constructor.
There's no dynamic binding in the constructor.
Neither in the destructor.
Well, that's not actually true. There is dynamic binding in the constructor. Because if you were to do this in 3 levels, and if you're in the middle level, I see what you're saying. There's no dynamic. Well, okay, I guess that's you can look at it that. You can look at it like saying there's no dynamic binding. Yes. So that's one way of looking at it. You can say that all method calls in the constructor are statically resolved. Yes. And so this sounds like a very strange thing to do. And it is definitely something that people find very confusing and that they do not expect. Java, on the other hand, well, let's see. So here's the same situation in Java. So I have an employee. I have a subclass manager. Here in the employee constructor, I construct the employee in the usual way, and I'm printing a logging message that says I'm constructing this employee. Here in the manager, here's my manager constructor. It seems like a normal constructor. It invokes the employee superclass constructor, so the name gets passed on to the superclass, and then it has the department string here, and it stores that here in what seems like the normal way. Why does this program crash when you try to construct a manager? Maybe it doesn't like managers. Few of us do. Yes? No.
It can't call manager.toString because the department has been initialized here.
That's exactly what you would like to say, right? So, but if you just look at what just happened in C++, wouldn't it just call this toString?
Except this is Java, so I'm guessing it works differently.
So in Java, it's the other way around. So in Java, in a constructor, virtual calls work. They work just in the normal way. So in Java, what happens here, we're calling super dot to, so let's work through it very slowly. So we're making a new manager. So we're in this constructor. We're now going down to here. So we're calling the employee constructor. That means we're ending up here. We're setting the name. Nothing can go wrong at this point. We're now calling constructing plus this. At this point here, it calls this dot toString. Right? Because the way that concatenation works, if you have a string and you have an object, then the plus operator implicitly calls toString on the object before it concatenates them. So we're calling toString. Now, in C++, we would be calling this toString, the one of the employee, because in C++, there is no dynamic binding in a constructor. In Java, we're calling whatever it is that this actually is. This is a manager, so we're calling this one over here. Let's see what it does. It calls super.toString, which returns the name. Nothing bad can happen. And then it calls this thing here. So it calls department.substring before it ever had a chance to initialize the department. And if you think about it, the Java way is simply wrong. It makes no sense to invoke a virtual function or a function on a subclass when the subclass is not yet constructed.
What's the workaround?
The workaround is to be very careful when you write a constructor in Java.
I mean, it's often we have something that we want to do at the end of the object construction.
Yeah.
And we want to ensure that the object construction is done before doing this. Is there a pattern
Well, see, the problem is not in the subclass, right? The subclass really doesn't do anything dangerous. The problem is that the superclass invokes a method which I have carefully hidden. And so what it unfortunately means is you should never, ever invoke a method in a constructor. Never. Do not ever invoke a method in a constructor, because someone somewhere might override that method in a way where they don't even realize that that method gets called from a constructor.
Never invoke an own method. A method.
Yeah, yes, a method of yourself. Yes, that's yes. And never invoke a method on this. Yes, because this at this point doesn't yet exist. This is clearly a design flaw in Java. They did not think this through. And it's interesting to ask, why did they not think this through? Obviously, Java came after C++. The C++ people went through a great deal of trouble, for once, to actually figure something out and get it right. But the Java people were so disdainful of C++. They hated C++ with such a wild and unbridled passion that they didn't even want to study it. And they didn't want to study its good parts. And so here the design of C++ was clearly right, that one has to be very careful about what a virtual function, what dynamic dispatch means in a constructor. And the Java people are clearly and plainly wrong. This is one of the few places where Java just got something wrong that they could have easily gotten right. It is not conceptually or implementation-wise difficult to turn off dynamic dispatch in a constructor, and they should have done that.
They still could do it now.
So could they fix it?
There's no code that relies on it because it crashes.
No, it might not crash. It might just act differently. This particular code crashes,
Yeah.
but other code, might just assume that those values are all still null. They might use them in some other way, and they might use the nullness to drive the code in some way. And that is a difficulty with Java in particular, because Java has made an unfortunate promise to the world that every program that was written in Java 1.0 will always be correct. So if you ever get to a point where you design your own language, don't make that promise. That is a very, very difficult promise to keep. So, so in Java, this is one of the things that one has to know. And I'm quite sure when you look at the Java Puzzlers book, you will find a puzzler that takes advantage of this. So here we have another thing that has actually happened to me. So I'm making myself a little array template here, and so I have an array. Array has a size. It has an operator brackets. Here I'm making one with 10 elements in it. I put a bunch of values in it. And when I do that, I find that some of the entries are 0. Not just A0, but a whole bunch of them are 0. So it compiles, it runs, and it has an annoying result. Why?
What was the problem? I didn't.
So some of the elements are 0. More than one element is 0.
Alright.
Yes?
Is there an equal operator on
No. No, there isn't.
They exist by default.
Yeah, so I did not redefine equals. But very, very good question. But why are you asking? Why is...
Because it's important.
Yeah, but specifically why? Did you notice that I forgot the brackets in here? So all of them have brackets except here I forgot the bracket 6. Okay, so here it says A equals 36. Why does it compile? Shouldn't the compiler notice this? So here's what happens. This thing here is a constructor with one argument, and a constructor with one argument is also a type conversion. So what does A equals 36 actually mean? It means take the number 36 and somehow turn it into an array of double. That's what it means, because we're saying A equals 36. And so now it's going to try this and say, how can it turn the number 36 into an array of double? I have a constructor that takes an int and returns an array. So it's going to call that constructor. That constructor will return what? An array of 36 zeros. So what's going to happen is we started out with A. It was an array of 10 zeros. The first 4 of them got filled. Then when it came to this first 6 of them got filled. When it came to this fateful line here, A was replaced with an entirely different array of 36 zeros. Why 36? Because here we're saying, oh, we wanted 36. That got into this constructor. That got us a new object, which replaced the old object. And then it goes on and fills 7, 8, and 9 with the remaining elements. This is super bad.
How do you come on, Lisa?
Yeah. So if one puts the magic word explicit here, yeah. So if you put the magic word explicit in here, then so over here. Then this no longer becomes a type converter, then it's only a constructor. So you can see here from the history that at one point in time, the designers of C++ had a bright idea. When you, as the designer of a programming language, have a bright idea, what should you do? The first thing you should do is take a cold shower, a long cold shower, and wait for the bright idea to go away. So the bright idea that they had was to say, oh, whenever there's this constructor with one parameter, we could also make that a type converter. And it sounded so good when they did this with the simple examples where they had like a fraction and they could turn an integer into a fraction. And it sounded so seductive because it meant they didn't have to introduce a new concept into the language. They didn't have to introduce a new keyword like type conversion or type conv or some such thing. They could just make a constructor do double duty. The constructor would automatically be invoked. And these kinds of bright ideas turn into really dumb ideas very quickly. When something gets done automatically, then it can get done too often, like you've just seen in this situation. And so 2 years later, and it took about 2 years, I remember this, I was still young then. 2 years later, they had to admit that this bright idea was so dangerous that what did they have to do? They had to come up with a new keyword, the keyword explicit. Now, programming language designers hate having to come up with a new keyword. Why? So if it breaks every piece of existing code that uses that keyword that used it previously. Every program that previously used explicit as the name of a variable or of a function or a class, God forbid, then could no longer compile. Now, admittedly, I don't think I ever had explicit, but I remember when templates were introduced.
Type-name.
What's that?
With type-name also?
Type name wasn't so bad because it's not a common word. But template definitely was a problem. That I remember I had to redo dozens and dozens of modules that used template for something else. Yeah.
The problem with type-name is the keyword was just introduced to avoid confusion. That is pretty useless.
It was, and that's the most embarrassing thing. It was introduced to paper over a previous design error. You know, it's bad enough to introduce a new keyword and make lots of people rewrite their code and be annoyed. But if the only reason was because they messed up in the first place, then that's even worse. So explicit really is a situation where you could see people mess up. And now 20 years later, people have to learn this explicit stuff. It would have made so much more sense to have some keyword, to have some special way of declaring type converters.
But then when Java 8 put the default for interface, it did break some code. Default was not
No, default is a keyword.
It was already?
In Switch, the default was carefully selected because, yes. So in fact, if you think of Java 5, when you had $extends x, extends was carefully selected because it was an existing keyword. And for a brief moment, when this was first introduced, when you had a wildcard in the other direction, it was actually written as x extends ? And I was there when this was explained at a Java 1 conference, and we all gathered around. I think it was Neil Gafter at the time who was giving the presentation, and people were complaining and that the programmers would find this very confusing. And one of the people in the room said, "Why don't you use super?" And a minute later, super was adopted into the language and for that usage. So keywords are always this issue. And another thing is when C++ first gained exception handling, 2 new keywords were introduced, right? Throw and catch. And Strustrup was not happy to introduce 2 new keywords. And he came up with an elaborate syntax where it only used throw. And so every time that now we say catch, he used throw. And it looked terrible. And afterwards, we all came to him and said, "This looks terrible." And Strustrup said, "But it's only 1 keyword." And so then I managed to convince the crowd that one could actually replace both throw and catch with static, and it would parse unambiguously. And that was considered so ridiculous that throw and catch are now in the language. So keywords are this nasty thing. So now we have explicit. So here, in fact, I have an explicit. So this constructor here cannot be used as a type converter. Here I'm constructing 2 doubles, so 2 arrays of double. And now I'm putting in some stuff into both of them. And it's not working. As you can see, that what I want to do is I want to put into AI and BI, I want to put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And when I ran this on my computer, B got filled with some seemingly random junk. So let's see where we could have gone wrong. So the explicit here means that the constructor here really was invoked in the normal way. So what's the constructor do? So it sets the size to, in this case, 10. That's this variable here. It sets the data to an array of 10 doubles. And what's operator bracket do? If you call it on the ith slot, it returns a reference to it. So when I say here AI, it should store the I plus 1 in here. Why doesn't it work?
Maybe in the constructor, new team, parental size.
Very good. Right? So in the constructor, it should have been brackets and not parentheses. Why did it compile?
Because we can, it's a constructor for all value. We can
Yes. Yes. So you have obviously gone through a very good program in the finer points of C++. That's excellent. So when you say new double of 10, this is, strangely enough, legal C++. It means to make a pointer to a new double and fill it with 10. Very good. What's that? Oh, 10. Containing 10, yes. So it makes a new double that contains 10. Which is probably not a syntax you have ever found useful. When is the last time that you wanted to allocate a double on the heap and put a value in it? Right? And so here comes what is a huge, huge crime in C++. And that is that in C++, there's no difference between a pointer to a value and a pointer to an array. So if you have a thing that's declared as a T star, then you know it's a pointer. You follow it along, you know that after that there's something of type T. That's how a normal sentient human being would understand a pointer. Right? A pointer to type T means you follow it along, and there you find a thing of type T. There are only two programming languages on the planet where that is not correct, and they're C and C++. So in those languages, it may be, or it might not be, that afterwards there's more of them. Of type T for sure. Or maybe not, as we will see on a later slide.
This is something that I always wondered why. When you create new int of 10,
Yeah.
brackets 10, and we don't know the size of this.
Yes.
There's no way to
Yeah.
find out recovering the size. But when we do delete brackets,
Yes.
the compiler does. It frees the amount of memory that was allocated.
Oh yes, absolutely. So if you allocate, say, a new T angle bracket 10, then the compiler, in some place, it's usually somewhere here, puts in the number 10.
Why can't we access it?
Because it would make it so that there would actually be a difference between a pointer to an array and a pointer to a single variable. They would have to come up with a new type, with an extension to the type system that was incompatible with C. So the original crime here lies with C. Right? In C, a pointer points to somewhere in memory and maybe a bunch of stuff afterwards. That was always a super bad decision. Now in the context of C, you might say it was a defensible decision because why did people program in C? They programmed in C so that they wouldn't have to program in assembly. And in assembly, of course, that was what C was designed for. Right? C was not designed for anything other than a high-level assembly. And that makes perfect sense because in assembly, of course, you have access to all memory and with whatever process instruction you have. And so C didn't particularly think that this was going to be a problem. You could just shoot yourself in the foot faster than you could with assembly, but it was it was for them not a particular difference in security. The problem with C++ is that C++ said, let's make an object-oriented programming language for the 1980s and beyond, and base it on C. Now, if there ever was a dumb idea, that was a dumb idea. I mean, why would you want to take base an object-oriented programming language that is there for large-scale programming and base it on C? I mean, that's like saying that you want to build a mass transportation system and that can ship thousands of people from place A to place B and build it on a Fiat Cinquecento. I mean, it makes no sense. And so because of that, we have this issue in C++ that where we badly need to be able to reason about types in a safe way, and we can't because it all falls back down to C pointers. There's no difference between a pointer to a value and a pointer to an array, and therefore, when we say something dumb here, where we say we want to this thing is a T star, but for us it is of course a pointer to an array. This thing here is a T star, but it actually is a pointer to a single element, and the type system cannot find this. The type system cannot say that this cannot possibly be the right assignment, so it lets it go through, and so the simplistic change between parentheses and brackets, that's cannot be caught by the type system. These are typos that actually happen in people's programs, and so they're very unfortunate. And so the ultimate reason for this is what is a huge design flaw, to say that a pointer to a single thing and a pointer to an array are expressed by the same thing in the type system. Yeah, so this is just a catastrophe. All right, moving right along. Since I've bashed C for so long, let's switch over to Java. So what do we have here? We have a list of integers, and into that list of integers we fill stuff in. So if you look at this line here, you'll notice that we add the numbers 1, 2, 3, up to 9. In this, we have a list of strings, and I'm adding in S1, S2, S3, up to S9. And now I'm removing this string here, and I'm removing the number 3. And afterwards, strings is this. S1, S2, you see the S3 is gone. What do you think is nums? So first it was 1, 2, 3, 4, 5, 6, 7, 8, 9. Now removing the 3. It is 1, 2, 3, 5, 6, 7, 8, 9. Why is it off by 1? It is the index. Very, very good. It is the index. Why does it pick the index? Why doesn't it remove the element? Yeah?
Remove, you have to put if because an integer is an index. And
how does it know that with an int? How many remove methods are there? Is there one remove method, or are there two? There are two. Right? It's the other remove method, because remove was overloaded. There is a remove of int, and there is a remove of t. It's a generic method, right? Remove of int goes by the index. Remove of t finds the object and removes it wherever it may be. Now when t happens to be int or integer, then those two overloaded methods conflict with each other. So, does that mean that overloading is bad? Yes, it does mean that overloading is generally not a great idea. So overloading is not a super good idea. It means that a library designer, such as the person who designed the list class, the library designer should have been careful. The library designer should have said, oh, it can happen that t becomes int or integer. And so it's a bad idea to give both of those methods the name remove. They could have called one of the methods remove at, and then this mistake would not have happened. Well, what does that say about a programming language feature, where the best advice is to not use it, to stay away from it because it might be confusing? In that case, really wonder how valuable is overloading. So for operators, overloading is hard to avoid. When you have a plus, we love our operators, we love the plus, and so we kind of want the compiler to figure out the right thing. For methods, it's not so clear that overloading is a super valuable feature. You have to have it in C++ and Java. Why? Why do you have to have method overloading in C++ and Java? There's only one reason why, if they can't just turn it off. Constructors, right? Because constructors are the only method where we don't get to choose the name of the method. Because someone somewhere made the really dumb decision that the name of a constructor must be the same as the name of a class. If they instead had given us a keyword constructor or some such thing, then that would not have been the case if we could have named constructors. And in fact, if you look at a modern C++ library, you don't see a lot of constructors. You see factory methods. Remember? Stream.off, optional.off, optional.empty. People like to be able to say what it is that they construct by giving the factory method an explicit name. So it would have been a really good idea to come up with some other way of doing construction. Anyone who's ever renamed a class knows that it's a pain. When you rename the class, you also have to rename the constructors in its definition. And it sounds like a dumb thing. So that was never a good idea. And that's the only point where overloading really is required. In other languages, there is no overloading. Like in C, for example, there's no overloading. And it's not usually a terribly missed feature. The only thing that one does really kind of like operator overloading. And so, of course, it's not really any harder to implement method overloading than operator overloading. But overloading is always a bit of a pitfall. And no one ever remembers the overloading rules exactly, right? I mean, do you really know if you have two functions with some overlap in C++? I guess you do know, right? But you're the only ones on the planet who knows this because you had it in Inf1. No one else does. Yeah. So overloading is a bit of a weird thing. All right. Back to C++. So here I have a vector, A. I have another vector, B. And I have some number. And I want to know whether B contains that number. Right? And so you use find. And it's kind of weird in C++ how find, you have to give a pair of iterators, the begin and end, and then you get back an iterator. That's just how the find method works in the standard C++ library. And now one of two things happens. Either P points to n inside the collection, or P, the iterator that's returned by find, is set to b.end. And so I have to check, is it set to b.end? And if it's not, then that means that inside B, I found my value for n. I found the n here. In this case, what I will do is I will close it out and put a -1 in there instead, and I will collect it in A. So the idea was that, so if B had a bunch of stuff in it, one of them was a 42, then I will push that to the end of A and replace it by -1 here. That way it's gone. So that's what I want to achieve. When I ran it, sometimes it dumped core, meaning the program came to an end and it said segmentation fault. Sometimes something worse happened. What could be worse than dumping core? With a malformed program, there's only one thing that is worse than dumping core. Not dumping core. Because when a program doesn't dump core and it keeps on surviving, it is very, very sick. So let's first of all see why. So the reason why we have this problem is here it should have been b.end and not a.end. Why did it compile with a.end?
Because it waits for true iterators and it doesn't check it.
Exactly. It can't check, right? The type system only knows is there's an iterator here and there's an iterator there. We gave it an iterator here. We gave it an iterator there. Compiler was happy, right? There's no way for the compiler to check this. Now, would anyone do such a stupid mistake? Moi. So this has happened to me in real code, not in this code, but in real code, where I copied and pasted a whole bunch of stuff. And then I needed to rename something, and I renamed all of the A's to B's, well, most of the A's to B's anyway. And so I was stuck with a couple of instances where I passed on to one of the STL calls these mismatched iterators. And now what actually happens in the machine? So we start at b.begin, which points to some vector. And this vector, say, it didn't contain 42. So it's past the end, right? So b.end points here. And what does the find method now do? It was looking for a.end, not for b.end. So it merrily kept going. As it happened, at some point, it found a 42 that was in some entirely different part of memory. There's a good chance that a 42 is somewhere. It is, after all, the answer to everything. So now what did our code do? So the pointer that was returned was not b.end. So this stuff got executed. Some other part of memory now had the 42 changed to -1. Hopefully it was an unimportant part of memory. Hopefully the program ended before that part of memory was ever used again. But if you are like my students, what always happens in this case is it works on your machine, and when I run your code, then it crashes. And so this is a horrible thing, right? This is just totally horrible. And in C, of course, that's how C works. In C, you can point anywhere, and it's up to the C programmer to control against this. But in C++, one doesn't really expect this. This is a library, for God's sake. This is a library that was designed with great amount of trouble by the implementors, of this whole library package. Why couldn't they make it secure? Why can't they make it so that it works like in every other object-oriented library, in every other object-oriented collections library? Be it in Smalltalk or Java or Objective-C or Swift or whatever language you can imagine. In Python, the way that something like find would work is find would operate on the object where you want to find stuff. It would operate on B, and you would say b.find of n, and then you would get back, presumably a position, int I, and that might be -1 if it's not in there. You might get an optional or some such thing. So you would operate on B. That's what object orientation is all about. Here it's a global function, and it gets these two iterators. Why? What made the designers of C++, the object-oriented programming language for the 80s and beyond, what made them say, we're not going to be using objects and methods or member functions. We're using a non-member function here. Why did they do that? They clearly could have done it the other way. They could have said, you know, what's B? B is a vector. A vector is a class. You've probably implemented vectors in your data structures class a little bit, right? You've implemented the vector, you've implemented pushback, size. You could have implemented a method find, or any of the other dozens of methods that are there in the standard template library. And the designers of the C++ library could have done the same. There were 20 years of precedent. So what made them not do that? What made them say, we're going to make this a global function. We're going to give it these two iterators?
Because it's faster?
No. I mean, the cost of finding is to look through the thing. And if it's statically resolved, it's the same speed anyway, so you don't even have a cost of a virtual function call. But so no, it's nothing to do with speed. They had a very good reason. And it's the reason you want to know if you to understand how the standard template library works. And you do want to understand that because it's better to use a library than not to use a library, right? The library has a whole bunch of stuff in there. It's all been debugged and optimized. So you want to use the library when you use C++. But why did they do it like that? They did it so that you can use the exact same methods as the exact same global functions with C arrays. So you can, when you have a C array and you want to find something in it, then you call the exact same find. You give it an iterator to the beginning. Now, the iterators have been cleverly done so that if you have plain C arrays, that an iterator is the same thing as a pointer. You guys didn't, this is not part of the, no? I was sure this was covered in Inf2 or somewhere. That, okay. So that's how it is. So this is a if you want, you can use it's and the templates really. There's only one find template. That find template, it says, you know, it's template T find, and what goes into the T. It's too bad that I didn't know that you don't know this. So it says template type name T T colon iterator or some such thing. And then it says find, and then again T colon iterator, T colon iterator. And then the code inside there does things with star P and P plus plus and P less than E to check whether it's less than the end. Or I think P not equal E. I'm not sure. I think it's P not equal E. And so all of these things have been super cleverly defined so that if T happens to be a pointer type, through the miracle of template specialization, anything on a pointer colon iterator is actually a pointer. If T is, on the other hand, a vector, then that specialization doesn't kick in and you get a vector colon iterator, whatever that may be. Or for a list, you get a list colon iterator, whatever that may be. But for pointers, you get straight out pointers, so you can use all these algorithms with C arrays. So you can say find. Now, how do you do the end iterator? You have to know what the size of the array is. You say A plus size. That is a pointer just past the end of the array. And so this is actually nice. You can use all of the functions, right? There's 100 or so STL functions. You can use them all on C arrays. You know, sort, find if, whatever, reverse, random permutation, whatever they give you, you can use them all on C arrays. So that was considered, yeah?
So why didn't they create a find method in the vector class and just call this one?
Yes, so this is something that happens. So these languages and these libraries, the way they are designed is that there is a committee of people who work together for months or years on end. And then one of them says, oh, I have this great idea. We're going to have this template, and it'll work on everything. It'll work on arrays. It'll work on anything that is willing to declare a : iterator. Just one code base. It'll be great. And then the other people in the room, they say, I guess this was called groupthink. And so what obviously is a really, really bad idea gets then promoted to a point where after a couple of years of standardizing this, then it just happens. So I remember when this did happen, and I showed it to a colleague of mine who knows more about object-oriented programming than I ever will know. And I said, oh, they're coming out with a standard library. Finally, we're going to get standard collections in C++. He said, show me. I showed him how the stuff works. And he said, that's weird. Why did they do it like that? I said, I don't know, but I guess because then it also works with plain arrays. He left the room. He said, I have no interest. No one but a fool would use a plain C array, an object-oriented code. Why would I want to use a library that embraces that use case? And he's, of course, totally right. Why would you ever, in code that needs to be maintained for a longer amount of time, that needs to be reasonably safe, why would you ever want to use a C array? You have vectors. You have, if for whatever reason you must have fixed size, you have arrays, the array templates. There's no reason to use C arrays in C++ code. If you're stuck on a desert island with a C compiler and nothing else, if you're doing embedded device programming where you don't want to have the overhead of C++, sure, you use C arrays. But if you program in C++, why would you ever want to program with C arrays? It doesn't make any sense. Sure, you might have for backwards compatibility, you might have to interface with code that uses C arrays. And in that case, it might have made sense to give defined templates for pointers and to make everything else into member functions. That would have been a reasonable thing to do. That way the member functions could have been safe and the templates would there be for legacy programming. But they didn't do that. And it was a crime. There's no other way of putting it. It means that they unnecessarily made it difficult to work with what otherwise would have been a nice library. So there is a bit of a remedy. There are some versions of STL that have checks in them against obvious errors like that, and you have to find them for your implementation and link against them. And I would actually recommend that if you do use STL, to figure out how you use the checked version, and at least during development, work with that, because these are obviously very nasty errors. All right, so here's another one where I'm not entirely sure whether this was covered or not, but I'll find out in just a minute. So here I have a very typical array class. Same as always, I have a pointer to the data that's dynamically allocated. Here, this time, I'm correctly allocating it with the brackets. And it's explicit. Over here, I'm deleting it in the destructor. And yes, I'm using the bracket operator so that it correctly calls the destructors on the elements. But there's something wrong about this class. And since no one is screaming, I'm assuming this has not really, either it wasn't covered or it hasn't sunk in. So let's make two arrays, A and B. We do something with them. And then for whatever reason, I say, I don't want A anymore, but I want A to be a copy of B. And then eventually they both get destroyed. Destruction happens in reverse order of construction, so B gets destroyed, and then A gets destroyed. So, but there is a real problem. And to see that, let's have the picture. So you have A has a size 10, has a pointer to 10 elements. We have B, size 10, a pointer to 10 elements.
There should be answer to this.
Okay. So what does A equals B mean?
That now A points the B element.
Yeah, notice that there is no operator equal defined here. So it defaults to the default version of assignment. So that means this 10 gets moved over that 10, no harm done. It means that this pointer here, the B pointer, now gets put into here. And so first of all, that means that A no longer points to this thing here. So it's still there in memory, but no one points to it. So here we have a memory leak. Remember, a memory leak means that you have a block on the heap that no one remembers. A memory leak is sad. They're very, very sad. There's a block of memory that no one remembers anymore, that just sits there. But it's only sad, it's not fatal. But now something worse happens. So B gets destroyed. What happens when B gets destroyed? Well, we can see what happens. It calls delete on this thing. So that means we follow B along. That's this block of memory. So what happens when you delete a block of memory? What happens in the processor when you delete it?
It's no longer allocated.
So do the transistors get cleaned out, or what happens? What physically happens? Here's what happens when you call delete on a block of memory, then you're giving it to the memory management module. You're telling the memory management module, here I have this block of memory, I no longer need it. What does the memory management module do? It says thank you. It says thank you, and then it links it together with the other blocks that it has at its disposal. Right? It keeps a long chain of blocks. Sometimes it tries to coalesce neighboring blocks or not. It keeps this long chain of blocks. And next time someone wants some memory, it looks into its chain of blocks and it says, here you go. So now we're going to delete this block twice, right? Because A also deletes it. What happens now? So the memory manager gets this block here. What does it do?
You no longer have access to it.
Right, but what does the memory manager do with the block that once handed it?
You can find it.
No, the memory manager is told, here you have a block at address 0x12345678. What does the memory manager do? It says thank you. And then it keeps the address of that block in a list of addresses that it keeps. So now the memory manager has somewhere in its list of free blocks, it says, oh, there's a free block at 1, 2, 3, 4, 5, 6, 7, 8. And later on in that same list, it says, I have a free block at 1, 2, 3, 4, 5, 6, 7, 8. Many, many thousands of instructions later, someone will ask for a new memory block. And the memory manager will say, as it happens, here I have one at 1, 2, 3, 4, 5, 6, 7, 8. Have at it. Many thousands of instructions later, some other part of the code will say, hey, I need some more memory, give me some. And the memory manager will look in its linked list and say, hey, I have one here at 1, 2, 3, 4, 5, 6, 7, 8. Have at it. And you're going to have two unrelated pieces of code that will both try to write on, not try, but actually will write onto the same block. How do you debug that? When this actually happens to you, when you find that your program randomly seems to destroy some parts of your data, how do you debug it? And even though that's a very hard thing to do. In San Francisco, the standard recommended approach is for the programmer to jump off the Golden Gate Bridge. It is almost impossible to debug such a thing. Right? Because the cause of the error is so far removed from where it manifests itself. And it's so random that it really is quite horrible. And so the moral is you need an operator equal. Does the compiler tell you that you need an operator equal? Unfortunately, it doesn't. You also need, by the way, a copy constructor. So as soon as you introduce a destructor into a class, you also need to have an operator equal and a copy constructor. Generally, it makes no sense to have a class with a destructor, but without operator equal copy constructor. Yes?
If we try to delete twice the same block,
Yeah.
actually it crashes.
Sometimes. When you're lucky, it crashes.
And it always crashes.
No, it doesn't always crash, because sometimes it crashes when it immediately happens after each other. So the standard memory allocator is rigged to recognize an immediate double delete. But it can't always crash because it would be too time-consuming for it to always look at all of its list of blocks. I mean, generally the heap has a very large number of blocks, and it would be inefficient to always look. You can so when people did a lot of C++, and I imagine it's still true today, there are some vendors who will sell you special debugging versions of malloc and free, where it'll then run slower, but it'll always tell you. And that's definitely very valuable during debugging. Yes?
That's something like background finding those kind of things?
Yes. Yes. And so in the heyday, there were plugins for like the Borland compiler that did these things, and for Visual C++. And so if that's your part of the business, you should get those tools. They're totally invaluable. And they're definitely worth whatever you need to pay for them. Because I mean, if you pay a few $1,000s for a tool, but it saves you from literally weeks of debugging. I mean, I've been involved in debugging sessions where for weeks we had to look for some double delete that happened somewhere in a code base with 1 million lines. And there's just no way of finding it. It's terrible. So you need an operator equal and you need a copy constructor. So many years ago, Marshall Klein, one of the pioneering C++ folks, said, the big three are destructor, copy constructor, and operator equal. It's not just a good idea, it's the law. So it really should be the law. The compiler should tell you that you need them. Unfortunately, it usually doesn't. And it makes it quite, in order to write professional level C++ code that manages resources, it's not an easy thing. In Java, you don't have any of these things. Why not? Why do you worry about this kind of stuff in Java? Number one, you have a garbage collector. Having a garbage collector is huge. And number two, you don't have object assignment. When you say A equals B, it's an assignment of the references to the object. It doesn't assign the actual objects. And there are very few languages these days where object assignment still works like it does in C++. It used to be very common, but nowadays it's generally recognized that reference assignment is simpler to understand for programmers, and it takes away this whole stuff. So,
just wondering,
yeah.
why, before we talked about binding the constructors, there wasn't available in C++, but why it's the same thing for destructors? You don't have
it's for the same reason that if you are...
for the constructor, there was a reason that the method table was not yet changed.
Well, the method table is just an artifact, but the ultimate reason is you don't want to invoke a virtual function that involves something that is not yet constructed or that is already destructed, because the destruction works in opposite order. First, the subclass gets destroyed, and like when a subclass gets destroyed, it might call delete on a pointer. You want to make sure not to use that pointer again afterwards. So that part, I think, works very rationally. And there's nothing particularly wrong about the C++ assignment and all of that stuff. It's just a lot of work. It's a lot of work, and it's something that's not intuitive, where the compiler can't really help you. And Now it's gotten more complicated with the move semantics and stuff. But it's just an area of immense complexity. All right, so just to show that Java has somewhat similar issues where there is something in the language where every implementer needs to do work and the compiler doesn't really tell you. So here you have a point class, a pretty standard point class, x and y, a constructor, an equals method, compares whether the two are equal. It is the right equals method. It takes an object, so it needs to cast it. Now I'm putting 1,000 points into a hash set, but that's actually not true. Most of those points, so the points are numbered from 0 to 999, but then I take the first number here, which goes from 0 to 10, and the last digit here, which also goes from 0 to 10. In other words, I put in every point 10 times. And now if I ask, what is points.size? What do you think I'm going to get? It's a set. So what I would think is if I add 100 points each 10 times, I would like it to be 100. But when I ran it yesterday, it was 1,000. And one could be unlucky and it could be 999. Why? And what's it have to do with that? The big three meant the user supplied one function, the destructor, and then they were forced to supply another two. That's just the law. Once you have a destructor, you must have an operator equal and a copy constructor. Otherwise, stuff isn't likely going to work. And in Java, you have the big two. Once you have an equals, you also need what? Once you have an equals, you must have a hash code. You simply cannot define operator the equals method in Java without also defining hash code. You must define hash code. It's the law.
Yes. My point on this, they know that. I think that hash maps, hash set are evil.
Yes.
Nobody should ever use that.
That is a very reasonable way of looking at it. That there's implicit contract in the library that people do this. They may be evil, but they're just so much more efficient that people use them. Right, a concurrent hash map. And so, as a practical matter, so this is bad, right? There's this implicit contract that you really must be defining hash code as well, because otherwise, what happens is that the hash codes right now it hashes by I don't remember what it hashes by, memory location or some such thing. I would imagine memory location, and so it will spread them all over the hash table into different buckets before it checks whether they're equal or not. And so this is totally bad. The compiler should kind of say something. It says, hey, how come you're redefining equals and you're not redefining hash code? But compilers don't usually do that. So these kind of contracts are not very great. All right, so now we're on to the single worst thing that you've ever seen in any language known to man. So I have a manager subclass and an employee superclass. And so here, I could write a method that takes an employee star and that fires the employee right now by just printing that message. And of course, I can pass it a manager star. That's how inheritance works. A pointer to a subclass can be converted to a pointer to a superclass. Here I have a somewhat different function. I want to fire a whole bunch of employees all at once. It's the way of the new millennium. So I go through all of them, and for each of them I say they're fired. What happens if my organization, like so many, has a whole bunch of useless middle managers who just sit there and consume valuable resources, I want to fire them all. Here. What will happen? Will it compile? Yes, of course it will compile. So a manager array can be converted to a manager star. That is conversion from an array to a pointer, a standard feature of C. A manager star can be converted to an employee star. That's conversion to a superclass pointer. An employee star is the same thing as an employee array here. That is array pointer duality. But these two features are so fundamentally incompatible that it's just a total catastrophe. It is just the worst thing imaginable. So let me draw you the picture. So you have this pointer to a bunch of managers. Here, let's say it's 3 of them. A manager has an employee portion. I want a different color. Okay, I won't. So it has an employee portion, it has some special manager portion, it has an employee portion, it has a special manager portion, and so on. Now I'm casting this thing here to an array of employees. So this is a manager star. Here I have an employee star. But that has a completely different memory layout, right? That would be an employee, an employee, an employee. And it makes no sense to make such a cast. It just makes absolutely no sense in the type system to say that a pointer to an array of managers is even remotely the same thing as a pointer to an array of employees. They're completely different things in their memory layout. And if you have an array of employees and now you're going to say, okay, I'm going to look at the second one, you expect to go by size of employee, and there you have the second one. Well, let's try it. We go by size of employee, and there we have something, some bits, some of which are supposedly the virtual function table. Nothing good can possibly come out of it. So this is so bad that it's just astonishing that anyone would take a programming language serious that lets you do this kind of stuff. Nevertheless, it's an executable outcome of two fundamental decisions. One of the decisions is to say the way we do object orientations is with pointers, and a pointer to a subclass can be cast into a pointer of superclass. Perfectly reasonable. The other one is to say that when you have an array, that all of the manipulation on the array we do through a pointer to its beginning element. The dumbest thing ever. And those two decisions are at a collision course that is really, really quite bad. So, how does one get there? Well, of course, all languages have bad parts that come usually through their history. Like in the history of C++, you start out with this really crazy premise to build on top of C. And so C++, because of that in particular, has more bad decisions than others. Some languages have really catastrophic, terrible decisions in them. And if there's one decision that's probably worse than any other and that's more responsible for more damage than any other in the history of programming languages, it is pointer array duality. It is simply dumb to say that when you have an array, it should be automatically converted to a pointer to its initial element. It means that your type system is going to be so weak that a huge class of errors cannot be detected for essentially no benefit. But that is the decision that the folks at C made. At the time when C was a high-level assembler, that was a defensible decision. When C morphed into more of a systems language, that became pretty bad. When C++ was built as a large-scale language on top of C, that decision became really quite bad. So you need to know this stuff, because if you don't know it, it will hurt you. It really is better to know and to fully understand what goes on. That is the reason why they torture you with in Inf1 and Inf2 with so many low-level details about C and C++. They don't do this just because they hate you, but because they really know deep in the guts that you must know this in order to use C and C++ responsibly. So you want to know these bad parts, and you want to stay away from them. Don't ever use an array unless you must. There's only there's two reasons to use a C array. Number one, if you don't have C++. And what's the second reason? If the instructor makes you. Yes. So the second reason will soon go away, so just don't use arrays. Just use vectors and stuff. So, stay away from languages with too many bad parts unless the good parts outweigh the risk. There are good reasons to use C. There are good reasons to use C++. But if those reasons don't particularly apply, why bother? So when I see someone who says, oh, I've just done this user interface in Qt, my first reaction is, you did what? This may make sense, right? If the rest of the project was in C++ for a good reason, then this might make sense. I know. But so it is important to know what is bad about a language. In a way, it's more important to know what's bad than what's good. And so the books here on the left here, by the way, this is the standard JavaScript book that you may have seen, the Rhino book. To the left is a very nice book called JavaScript, The Good Parts. Note how much thinner it is. All right, I'll leave it at that, and I hope you found it amusing.